This is going to be a follow-up talk from Ricardo's one this morning, and where I'm going to dive more deeply into one of our latest works, which is this one. So the plan is I'll just summarize very briefly what Ricardo says about rare dense clusters of solutions. Our original analysis started on discrete weights, and then in this paper that I mentioned, we moved towards the continuous case where the high local entropy regions that he was mentioning will become wide flat minima, essentially. And then in order to do that, I will tell you about a little trick that we have found out about, and I think it's going to be nice for at least for people who use replica theory. The trick is that we can recover this large deviation analysis by exploiting the one replica symmetry breaking formalism. There's a connection there that I'll try to explain. Then I'll move away from replica theory and to message passing, how to use belief propagation as a tool to study the landscapes of solutions, and also how to turn it into an efficient solver. And then more on the algorithmic side, the role of cross-entropy, of the cross-entropy loss function, and how to transform a very greedy algorithm into an algorithm which actually gets into wide flat minima. And finally, I'll conclude with some numerical tests, and in some cases where we also deal with non-random patterns, which we cannot analyze analytically, but we can at least test our intuition in a situation which is close, at least as close as we can get to the analytical calculations. And finally, a final experiment in which we take the non-random patterns and we randomize them again as a way to bridge the gap between these two situations. Okay, so the kind of models that we can study in detail analytically are these sort of things, so a simple perceptron or shallow networks. In particular, I'll focus mostly on this one, even though we did some numerical experiments on this architecture as well. The patterns in the analytical studies are random, the inputs. We study networks which have non-trivial landscapes, so in this case, discrete networks, in this case, discrete or continuous. I'll focus on the continuous case. And throughout the talk, I'm going to assume that the transfer functions at the first layer are step functions. So even though we did study ReLUs, as Ricardo said, here I'll only consider step functions, no bias. One important thing I want to point out is that the weights are always going to be normalized. That's going to come in play later. And the second weights, the weights of the second layer are fixed to 1. So this is the model, the models that we study. Now, again, a quick summary of the main idea of the local entropy measure is that we perform a large deviation analysis, and we want to bias the statistical measure, moving away from the Gibbs measure and biasing the statistical measures towards dense regions, either wide and flat region, which we do by defining this potential. Here I am the more general version with the temperature, so we call it local free entropy if you want to be precise. That's a potential that depends on the configuration, and the expression here can be interpreted more or less like this. We want, except for the log, what we are doing is we are counting all configurations that are within a certain loss or energy, if you want, and that are within a certain distance from the reference. So this W tilde is the reference, and we move that around. We have two control parameters, beta and gamma. Gamma determines the distance, beta determines the energy levels that we are exploring, and then we want to optimize over this potential. So we basically consider this expression, the usual Gibbs measure, but with a different potential, a different inverse temperature that we're calling y, and we send that to infinity. So this is the setup. And again, as Ricardo was saying, we can take this, these are just the two formulas that I've already shown, and now we can take the partition function, and by considering that the parameter y, we just restrict to integer values of this parameter y, and by doing that and purely algebraic manipulations, we end up with this alternative expression, which gives us an effective Hamiltonian of an effective system, which is actually a replicated system with a number of replicas and an interaction term. And graphically, this looks like this. You have your original factor graph. By the way, this is general, so whatever the factor graph is, whatever the problem is that you're studying, the way to go from a usual description to this local entropy description that we call robust ensemble is to just take the original system, replicate it a number of times, and then these circles represent variables of the problem. So we add an external set, an additional set of variables, the reference, this is W tilde, and with an interaction between each variable and the corresponding replicated ones. So, and if we can simulate that, then the reference will move in the local entropic landscape rather than the original energetic landscape. And so if we look at this connection scheme, if we just focus on one of the variables, you see the replicas there and the reference here. So we have this scheme, which, I mean, I can represent sort of in this way. So it's a star-like shape, the reference in the middle and the replicas around, connected in this way. What Ricardo was saying is that one can have an alternative connection scheme, and this leads basically to quantum Monte Carlo. And now, the first thing I want to point out is that there's a connection between this and the usual one-step replica symmetry breaking formalism. And the connection starts from an ergodicity breaking scheme, which was done by Remy in 1995, where he showed that in order to get to the one replica symmetry breaking scheme, you can do that by adding a weak external field, then doing some manipulation. Again, you see here I've highlighted that the parameter m here becomes integer, then one does additional manipulations, and then that ends up in an expression in which it says we have to study the statics of m interacting systems with an attractive coupling between themselves. So this is exactly what we are doing. The difference is that in order to get back to the equilibrium measure in the one-step replica symmetry breaking formalism, you need to send this field G to 0. And in our models, at least in some of our models, if you send this field G to 0, you lose everything. You get back to the original description. Whereas if you don't send this to 0 and instead you send this m to a large value, you get our robust ensemble description. So to summarize, we have essentially a recipe where we do the same exact computation as the one replica symmetry breaking scheme, but the interpretation is radically different because the replicas in our case are real and they're not virtual. We don't send the field to 0, and instead we fix it, and we don't send we send the number of replicas to infinity, or at least to some large number, like 5 or 10 already. That's yeah.
What was
the G is what was the field here, and it's essentially the same thing I'm calling gamma in my other slides. So the interaction. So yeah. So and the m value, which was in the other scheme, is the usual Parisi parameter. In our case, it's y, and it's the same. It's the same. There's one-to-one map, except for the way we interpret it, and therefore where we are looking for solutions. And one other connection between this scheme and the one replica symmetry breaking scheme and our own, the large deviation one, can be found by trying to write the cavity equations. For example, one takes the textbook definition of the one replica symmetry breaking cavity method equations, the general one, and by a slight adaptation, one finds exactly, one recovers exactly our own, the robust ensemble description. And this can even be made efficient computationally. The thing is that when we try to use that as a solver, it doesn't work very well because of symmetry breaking effects, but there's, at least at 0 temperature. But there are alternatives to that, as I will show, that work around this problem, even though they are more approximate, let's say. So, in practice, the general case is one can just compute the 1RSB action as one would usually do in this sort of problems, or even look it up in the literature, which is what we did. Instead of, so one in the 1RSB description, one gets an overlap parameter called Q1. We express that in terms of the distance between replicas that might need a change of variable or not, depending on the problem. We solve the usual saddle point equations, except for one. So we have the usual scheme, and we remove one equation. And Q1 is going to become an external parameter. And then we need also to deduce the scalings in this limit here, which might or might not be trivial. And the result is, this is going to neglect some replica symmetry breaking effects, but still the result is going to be that we get a description of this sort in which the statistics that's being described is the large deviation statistics of the high local entropy regions. So we applied, yeah.
But what happens with the G? Because you don't have the G, as you said, in the usual 1RSB scheme.
Yeah, so yeah, so in fact, so in the original, that's another external parameter in our description. So in the original 1RSB description, you introduce this G and you send it to 0. Yeah. In our case, you introduce this G and you just fix it to some value.
Okay, so you have Q1 and G that is fixed in some...
Yes, yes, exactly. Well, sorry. It's the same. They are conjugate. Q1 and G, they're conjugate one to the other. So you either fix G or Q1. It's the same, effectively. Yeah, sorry. The other thing is why... Yeah, so this...
so there is no G there?
No. Yeah. If I fix Q1, there's no G. If I fix G, then it's going to give me an effective Q1 that I can use, or an effective distance, yeah. Okay, so this is sort of technical, but also I think interesting and useful in practice. And in fact, we used that to just consider a committee machine, the tree-like committee machine that I was showing earlier, and we just started from the 1RSB solution, which is known. We took it from this paper here, and instead of solving everything, we just fixed Q1, took this limit here in the 0 temperature limit, and that was it, essentially. That gave us the volume of the solutions at a given Q1 at a given alpha. And we could compare that, since we don't have an absolute scale for the volume, we compare that to the alpha 0 case, which is the case where everything is a solution. So in the end, this is the fraction of the volume at a given distance that solves the problem, that has a zero loss, let's say. And we take the log of that, renormalize, and do the analysis. And the result of the analysis is shown here. Now, these are different values of alpha. This is for a committee machine with 3 units. And the fact that these curves here tend to collapse onto the 0 line, we interpret that as the presence of wide flat minima. Because when you have a region of Q1 here, when Q1 is close to 1, it means that the distance is small. And therefore, in this region here, we are looking at regions of a given distance in which almost everything is a solution. So it's a very flat lake, as Ricardo was saying earlier. Now, of course, the size of the lake depends on alpha, but it's always there, at least according to this calculation. It's always there, even not only for the k equal 3 case. We also have the limit of large k. We effectively find the same situation. And again, as Ricardo was mentioning, this seems to be structural for this kind of models, in that if you again repeat exactly the same computations, but you substitute the final output from the sign of the sum, you substitute it with a product, and this is also called parity machine instead of a committee machine, then you repeat the computation and you would get a flat curve, just exactly a flat curve. So you don't see it reaching the zero line there, meaning that there are no wide flat minima. So this leads to the claim that the existence of this wide flat minima is some sort of structural property of the model, even without, I mean, this model, they don't have anything to generalize at all. The patterns are random. So the origin of this phenomenon should be, in a sense, structural to the architecture. And it's an open problem to actually make this statement more precise and determining whether neural network models are somewhat special and how. Okay, so this was for the replica theory. Now, that gives us the general description, the say average description. Now, if we want to analyze single instances, then we need to move to to message passing, essentially. We used BP, and just again as a technical note, we used BP instead of approximate message passing because it allows us to have a slightly less approximate solution. We can get away with a, and since we are working with systems that are not so large, this turns out important just for numerical reasons. So, but it's basically the same algorithm in a sense. In this case, messages are distributions. However, we only need to propagate 2 quantities per message, so we can make this efficient enough. One important thing is that we need to control the norms, which we do by introducing a self-adjusting external field. And another important thing, this is a technicality, but this is an important tool, that when we can use this algorithm to explore a region around a given configuration. So for any given configuration, we can explore the landscape at a given distance by just using an extra field in the direction of the chosen configuration. And that allows us to measure the volumes around a given configuration on a single instance of a problem. So that can be used basically as a tool to verify this sort of picture or measure this sort of picture, but on particular instances and using particular solutions found however they are found. So measure the flatness of the solutions and so on. Okay. On top of that, we can also start from belief propagation and use again a general, say, machinery, which does not depend on the model, to transform that into an algorithm that finds one wide flat minima. And the idea here is to basically to run belief propagation on the factor graph, the replicated factor graph that I was mentioning before, and then to assume some symmetry. And I'll just show how it goes. This is one variable. It's replicated a number of times. So this on the top here, there would be the rest of the factor graph, everything that defines the model. But then here we just have a replicated variable, and here we have reference variable, and then we have these interactions, which I'm sorry, I realize now that I called it lambda instead of gamma, but it's the same thing. And then we have messages going propagating along these edges. And we can use a general formula, which I'm not going to get into. The notation here is I come up with this notation. Just the only point is that this sort of operation is general. We assume that all the messages going in corresponding positions are the same because these replicas are all the same. And in the end, we end up with a formula which, given the message coming out from that node, gives us the message incoming to that node. And this is not a factor node in the usual sense. It's what I'm calling a pseudo factor node, and the net effect of this is that it's self-reinforcing the configuration of this variable, whatever it is. And one can just choose values of these parameters and run BP and get a description of the, at least approximately, but with good approximation, of the large deviation measure. And if we then take this algorithm and gradually increase, say, lambda, and converge, and then increase it again and converge, and so on and so forth, then we can, in the limit of this, when this parameter gets to infinity, this variable will get completely polarized. We will have ended up in a solution, in a configuration, let's say, and then we can analyze that configuration. And the result of doing that is the quite efficient algorithm. It's an algorithm that, at least on 3 committee machines, has the highest capacity. That is, it gets to the largest alpha of all the algorithms, alternative algorithms that we have tested. And it even works well within a phase in which standard belief propagation doesn't work, so even within the one replica symmetry breaking phase. And it finds very wide minima, as you can see here. Now, this is more or less the same curve that I was showing before, except that it's plotted as a function of the distance from the solution instead of the overlap, but it's just the same thing reversed, essentially. And, well, you see it's rather flat here, let's say. And this is the same measure as before. So the problem with this algorithm is that so far it only works with uncorrelated random patterns. It might be amendable to use, say, at least random patterns with some correlation structure, but we didn't do that so far. And also, it works very well with tree-like architectures, but with the fully connected architectures is a little bit more tricky. Still possible, but more problematic, let's say. So this algorithm works great, but has these limitations so far. So one can consider alternative algorithms. And in particular, one can consider, say, the usual algorithms that have been used in machine learning. And one thing that we then went on to analyze is what's the role of using the cross-entropy loss, which is by far the most popular loss function used in machine learning today for classification problems. But it's not entirely clear, I would say, why it's so effective compared to other possibilities like, say, mean square error or this sort of thing. So in a binary classifier, the local entropy looks like this, where X is the pre-activation. And the cross entropy looks like this, and where X is the pre-activation. And here I have introduced a parameter gamma, which is not usually there. And the reason why I have introduced this parameter gamma is that I want to use it as a representation of the norm of the weights getting into the output layer. So if you think of the pre-activation and you take the weights and you normalize them and you extract the norm, then this gamma is going to have the role of the norm. And normally, one would just not control the norm and allow gradient descent to control it, so to just drive it. But in this case, I want to fix it myself and keep X normalized, so just as a way to control it.
So, this is binary, the weights are binary, or?
The weights, here the weights do not really matter. If the weights are binary, then the normalization is automatic. If the weights are not binary, then I normalize them myself. This is just the last unit, and you compute the pre-activation, and then you apply that formula and use that as your energy function, essentially. So,
but you're saying this again, this is continuous. binary?
Well, the energy looks continuous in principle. If this was binary, then this would have only discrete values, but then in the limit.
Which problem you are trying to solve?
Okay, now I'm back to the simplest case in which we are going to study the binary perceptron case. But right now I'm only speaking about the properties of this function because I just wanted to clarify a few things about the notation I'm using, in particular the role of this gamma here. That it's not what you usually see. So I wanted to spend a few words on that, and we want to control it explicitly. So if we just look at this function, how it looks like when you change gamma, it looks like this. This is for small gamma, and you increase gamma, and you get to this. So this region here, where x is positive, is the region where the pattern has been classified correctly. So in the limit of large gamma, these curves become a negative ReLU, essentially, so it becomes exactly 0 in this region. However, when gamma is not infinite, you get a little bit of residual effect here, which means that even for, say, a correctly classified pattern, there's going to be an energetic push towards increasing the pre-activation, which means when you do, say, gradient descent or these sort of things, which means that in a continuous network, the optimum of this function is going to always to be with infinite x on the right, or equivalently, if you normalize x, it's going to be with infinite norm. So what we did is we studied this loss function on the simplest case, which is the binary perceptron. We did the replica analysis of that, and we studied, say, the local landscape around the minima of this loss. And what we found is that the minima of this loss end up more or less in the middle of these high local entropy regions, as long as the norm is within a certain range. It's shown here. So here is more or less the same curve as the previous one that I've shown, except the local entropy is not normalized. So here, instead of comparing the curves to 0, we need to compare them to this gray curve here. And when the other curves get on top of that, that's where the high local entropy regions are. And you can see that, say, there are situations like this gamma equal 1, the yellow curve here, where it doesn't really work. There are other situations when you send gamma to infinity, where it also doesn't really work. But with intermediate gammas, it does work. Okay, so it does work in the sense that this algorithm works, this loss function works as a reasonably effective proxy for the local entropy optimization. Okay, now this is for a very, very shallow network. For deeper networks, there should be more things to be said. I think I should move on, though. But this robustness effect that it's introduced by the cross-entropy is mostly limited to the last layer. So in a sense, it helps finding these more robust regions, but it's not exactly equivalent to optimizing the local entropy optimization that I was mentioning before. Okay, this I'm going to skip. Another algorithmic approach is this one. In this case, what we did was we took an algorithm which is, I mean, kind of not exactly new. It's from 1989. It's not great, not very well known. It's called least action learning, and it's an extension of the perceptron algorithm to the case of the committee machine. It's a heuristic extension. There's no proof that it should work, but it actually does work very, very.
I think it's from 1964 or something like that.
Oh, really?
Nielsen's algorithm.
Ah, so we should update our reference then, because I mean the earliest one we could find was this.
Yeah, I mean the computer machine was invented by Niels Nielsen, who actually died this year. He was at Stanford, and he came up with the, find the unit that would.
Yeah, the least wrong unit.
Flip the.
Ah, so that. Thanks. I'll ask you for the reference later, so I will update that. Thanks. Okay, so it's even older than what we thought. Anyway, the way it works is that, as Jan was saying, that you just present a pattern, you check whether the classification was correct or not. If it's correct, you do nothing. If it's wrong, then you just look for the unit that is the most easily fixable. And you apply the perceptron rule to that. And this is very greedy, it's very fast, it has actually very high capacity, more, I should say, than stochastic gradient descent, at least on random patterns and committee machines. It's interesting in a sense because it's not gradient based, and it doesn't require that the network is differentiable. And however, it ends up in very narrow minima that we measured by using Belief propagation, as I mentioned before. Now, if we take this algorithm and just do a very simple trick to replicate it, basically, so we have different replicas that operate in parallel, but then we add an interaction between replicas that gradually pushes them together towards one another. It's still a fast algorithm. Of course, you lose at least a factor which is as large as the number of replicas that you are using, but it finds much wider minima, as I'm going to show in a second. The problem of this algorithm is, of course, that it's unclear how to extend it to deeper networks, which is why it's not very used nowadays. But the interesting thing is that you can take an existing algorithm and make it more robust by just this simple trick, we think. So now coming to the numerical experiments part. We did the first batch of experiments with random patterns. So we started with 3 committee machine with K9 in the units. We set up a number of patterns which is low enough such that all our algorithms could work and find solutions. And the setup here is as close as possible to the theoretical analysis. We try to get as close as possible to the theoretical analysis. And we tested 5 algorithms to find solutions. Now, 3 of those I've already described. It's focusing BP, then these 2 variants of the least action learning algorithm. And then we compared that to the stochastic gradient descent with cross-entropy loss. And we tested that in 2 different settings. Now, these 2 algorithms, the stochastic gradient descent, they required a differentiable network. And since we are using step activations, that's not our case. So what we did was actually to use activations in this network, which are tan h of beta x. And again, you can interpret beta exactly like before, x like a pre-activation and beta as the norm of the network. And in the limit in which beta gets large, the network, the transfer function will effectively become a step function. So it will get back to the previous situation. And so what we end up doing is applying this algorithm, but controlling the norms ourselves. That is, I'm calling beta and gamma the norms, because that's their role. And what we do is we polarize them gradually, and we do it either quickly or slowly, essentially. And then at the end, we find solutions and compare the local volumes, the spectrum of the Hessians, and so on. So the outcome is is shown here. There are a few measures. Again, this is the measure of the normalized local entropy. So the flatter curves are the ones with the larger volumes. This is the distance. So this is the least action learning algorithm. We could not continue the curve up to here. It should get up to 0, but we just couldn't, for numerical reasons, get there. But you see that it has very small volumes, meaning this algorithm is very quick, but it ends up in a really narrow regions, small volume regions. Whereas the other algorithms find much flatter solution. In particular, I want to point out that going from this least action learning to the entropic version, the replicated version, the yellow one here, gives you a much larger volumes. And we see a sort of ranking of the algorithms at this level. I mean, the focusing BP is the one that finds flattest solutions and so on. We see that going with a cross-entropy SGD, going more slowly helps a little bit. This is also observed when we look at the full spectrum of the Hessians, which is shown here. Now, again, we wanted to measure the Hessian because that's what people usually does in the machine learning community. So we wanted to relate this with the spectrum of the Hessians. And however, again, Hessians require a smooth function to be computed, and so we use the same trick as before. We turn the step activations into hyperbolic tangents. So just again, we computed this, and then we changed the value of beta. Essentially, there are some more technical details to this, but I'm not getting into that. In any case, one can observe that there's again, if one looks at the eigenvalue, the positive ones are the relevant ones, to where, say, in particular, the maximum one gives you the steepest. It tells you the direction, how narrow the loss function is in the steepest direction, and FBP has smaller eigenvalues than entropic LAL, and then slow cross-end, and there's slow SGD and fast SGD. So the ranking here, and I mean, here you see LAL, the ranking here is exactly the same as this one. So far so good. This is all on random patterns. Then we tried to test the same thing on non-random patterns, but again, trying to get as close as possible to the theoretical situations that we have analyzed. So what we did this time, we used a fully connected committee machine, again with 9 units. We chose the fashionist data set and selected 2 classes out of the 10 that are present there, and we chose them to be, let's say, hard but not impossible. So discriminating dress versus code. So it's a binary classification task, and this choice gave us a good range of generalization, of different generalization error, as I'll show in a second. We binarized the patterns, and so we ended up with a situation in which, compared to the previous one, patterns are binary and also balanced, just like before, but differently from before. They are biased, meaning that each pixel, each input can have a different, I mean, it's not 50% up or 50% down, on or off, it's biased. And also there are correlations within each pattern and between the pattern and the desired label. So in this case, we could not test belief propagation because of the correlation in the patterns. So we tested only the other 4 algorithms, and we repeated the same tests as before. And you see the ranking is the same when you look at the volumes, same as before, more or less. And in particular, the differences are even larger. I want to point out, again, 2 most important things is that when you look at least action learning, it works very well, but it finds very narrow solutions. However, if you replicate it, it gets to much wider solutions. And also that if you compare the 2 settings of SGD with cross-entropy, it's very convenient to go to control the norm and make it grow more slowly in order to find solutions which are wider. Yes?
Just to clarify, how are you computing the local entropy here?
Here with the belief propagation. So I solve the problem with the algorithm, then I take the solution, and I run belief propagation with an external field with a bias towards that solution and an intensity which changes.
Yeah,
and
so it's the same as before. But at
yes.
this level, the fact that the patterns are correlated is not bothering.
Well, I mean, that's true, but that's true, but at least, let's say, at least for short distances, it shouldn't matter too much, probably. If the local structure of the solution that you find is more or less flat, then the idea would be that the approximation should be, well, let's say, at least more or less good. Yeah, but it's true that we don't really have control over this. So that's the intuition. This measure, it's approximate, and in any case, this gives us a sort of ranking, and we can compare that again with a maximum eigenvalue of this. Each individual point here is a different solution, so a different run of the algorithm on the same data. And you see that now, this time, we can even compute the generalization error. And first of all, one interesting thing is that the generalization error here ranges from 0. Say up to, let's say, 5% to 20% almost. And all of these points here are solutions to the problem. So they are all equivalent from the point of view of the energy, let's say, but they are quite different in their generalization property. And the eigenvalue, the maximum eigenvalue, so some crude summary description of how the local landscape around that solution looks like, is pretty much correlated with the test error, as you can see. And also, the ranking of the algorithms is the same as seen here. Okay, so all of this, again, it's not 100% under control, far from that, but it gives, at least it gives a consistent overall picture. And now the one further test was, okay, so wondering how important is the structure of the data, because this data now is biased and correlated. So what we did is, again,
can I ask you a question about the previous figure?
Sure.
It seems that it's not really the eigenvalue that controls the test error, but it's the algorithm also, right? In the sense, it's not that they line on over, on a line where they go up. It's more steps depending on which algorithm you use, if I understand correctly. Even though it's clear,
well, I don't know.
The more you go to the right, the higher it is.
Yes.
It's by steps. It's like, so it's not only, it seems that the learning that you use matter also, not only what you see at the bottom.
Well, you might say, these two curves here are the same algorithm with different settings, if you want to put it that way. So yeah, in a sense, that even with the same learning algorithm, different settings, you can obtain significantly different results, both in terms of, in terms of the volume, in terms of the eigenvalue, in terms of the error. Yeah, so the relation between maximum eigenvalue and generalization error is not perfect at all. It's very noisy. It's just a qualitative.
The question is, I think the other way around.
Yeah.
If you have the same more or less maximum eigenvalue, can you have...
Well, but you see here you have two algorithms which are radically different from each other. It's just the cross-entropy SGD is low and entropic lull, and they are more or less on top of each other in both cases. So, it's 1 point for a particular data set and so on and so forth. But that's the evidence that we have so far.
Can you say how do
yeah.
you get the Hessian if it's binary?
Yeah, so the Hessian, we do it by using this, these soft activations, and then we choose beta such that it's as large as possible to get close to the step-like function, but not too small such that we degrade the performance, the classification performance. So it's a criterion that we had to come up with in order to measure Hessians, which we did again because just to compare with, say, the existing literature in machine learning.
But the result about the maximum can go.
Yeah.
But will these results are sensitive to data?
Sorry?
Will these results be sensitive to data?
Oh yeah, absolutely. Look at this. These are the same network, same function, everything is the same, but with two different betas. So the maximum eigenvalue here could be 20 and here could be 2000. But what we did,
But you can scale. I mean, there is some number of beta there or something.
I'm not sure you can scale because this beta, I mean, it's non-linear.
No, but
Well,
forget about the absolute scale. I'm
Yeah.
asking, go back to
yes,
here.
yes.
I mean, forget about the absolute scale.
Oh, here we use the same beta for all.
I know, but now you change beta.
Yes,
The scale may change, but
Yes.
the x-axis.
oh, well, we tested that. I mean, we are showing one beta, but we have tested a few values, and it's the ranking, let's say, more or less stays the
That's
same.
what I'm asking. So
Yeah, yeah.
in that sense, it's not sensitive.
Yeah, it's not too sensitive to beta. So of course there are going to be extreme cases where everything collapses or whatever, but it's not too sensitive to beta. Yes. Just in a sense, this beta is similar to the distance here. I mean, very vaguely. So you see that there are some crossings here, but depending on the distance, you get a ranking of the algorithm that is basically the same for all distances. So it's sort of the same situation. How much time do I have? Okay, yeah, I'm almost done. So finally, what we did was we took exactly the same data as before with the same setup, with the same algorithms, with the same parameters, everything is the same. But what we did was we took the patterns, and for each pixel, we shuffled them across the patterns. So we just take one pixel in one pattern and send it to the corresponding position in a different pattern and so on. So what this does is that all the biases are kept, but all the correlations are destroyed.
So you shuffle from between patterns.
Yeah, yeah. So now you lose the correlation inside the patterns and between the patterns and the outcome. So now it's the sort of the same statistics in terms of the biases, but the different statistics in terms of correlations, and there's nothing to generalize. And the problem, of course, becomes as a classification problem just for information theoretical reasons, or at least with information theoretical argument, you can say that it becomes slightly larger. The results are more or less similar, except that this entropic lull is affected more than the other algorithms. That's unclear. The reason is unclear. But what remains true, importantly, I think, is that, again, when you go from lull to entropic lull, there's a big difference in terms of volumes and in terms of eigenvalues. And also when you go from the fast cross-entropy to the cross-entropy SGD to the slow cross-entropy SGD, again, there's a big difference, both in terms of volumes and of the Hessian spectrum. And final test that we did was we tried to measure now the robustness with respect to perturbations of the input. So what we did was we tried to introduce noise in the training set, again, in order to compare the non-randomized data set with the randomized data set on something that resembles the generalization, let's say, capabilities. And in order to do that, we corrupted the data in a way that tries to keep the statistics there. And again, the randomized data set is harder, the volumes are smaller, but the picture is pretty much completely consistent with the ones that all the other pictures that I've shown before. So this is it. In conclusion, it seems to be that wide flat minima are a structural property of neural networks, at least the shallow ones that we have analyzed, but we have reasons, I mean, numerically, reasons to believe that it extends to deeper architectures. And when I say structural property, I mean without even considering structure in the data. This wide flat minima, they seem to generalize better, and this has also been observed by other groups who have worked with realistic data sets and larger, let's say, more state-of-the-art networks. There are some algorithmic techniques that can help finding such minima, and some are very well known and widely used, like using the cross-entropy as a loss, using ReLU as transfer function, as Ricardo was saying. Some techniques are not exactly well known or widely used, like using this entropic principle. Now, open problems is what the role of the pattern structure, which is still to be investigated in more detail. And finally, we are trying to work to we are trying to address the problem of going to deeper architecture. This is very much working problem. And then something that we are not actively working on at the moment, but would be very nice to know from the theoretical side, is to get a detailed description of the geometrical structure of this high local entropy wide flat minima, because I mean we describe them roughly as lakes, but we have reasons to believe that they have a very detailed and rich internal geometrical structure. And well, there's also some other more open problem from the say algorithmic side, but I'll stop here. Okay.